Okay, welcome back. Let's talk accuracy and precision. Whenever we make a measurement, we need to use these terms as well as error. And so, accuracy is how close is the measurement to the actual or true value. And precision is when we make more than one measurement, how close together are those measurements? And it does not matter for precision what the true value is or what the expected or accepted value are. So to evaluate the accuracy of a measurement, the measurement must be compared to a correct value. To evaluate precision, you need more than one measurement to compare those together. So if we look at this dartboard that we have here, we have all the darts in the very first picture centered right on the bullseye, and they're very close together. So this would be good accuracy and good precision. It's good accuracy because it is at the center of the bullseye, and it's good precision because they are close together. In the middle picture, we have poor accuracy because the darts are not down at the bullseye. They are all up at that 20. However, it still has good precision because all of the darts are close together. In the last picture, we have neither good accuracy nor good precision because the measurements are not close together, nor are they close to the center of the bullseye. So, determining error. Typically, if we want to, like my husband loves to barbecue, he wants to know how accurate his thermometer is. He's going to take it and he's going to boil some water on the stove and he's going to check to see if that boils at 100, or in the case of an analog or a Fahrenheit thermometer, at 212 Celsius. Then he's also going to put it in water with ice in it, let the water get down to the freezing point, and it should read 32 Fahrenheit. This gives him 2 points on his scale that tell him that the thermometer is reading as it should. So you have to compare it to a known value. And since it should read, in this case, 100 degrees, but it's reading 99.1, then we know the error would be the subtraction of those two. So determining error is just the experimental value minus the accepted value. And we typically do this in the lab, but we do it as percent error. So calculating the percent error means that we would divide it by the true value. So the boiling point of pure water is measured to be 99.1. Calculate the percent error. So we know the accepted value, we know the experimental value, and we are going to take the error or the subtraction of those two, and we take the absolute value of it. So we make it positive. If it's negative, it's positive. If it's positive, we leave it positive. And then we divide by the percent, by the accepted value times 100 to make it into a percent. So this case, it would be 99.1 minus 100, but we take the absolute value of that, so we get positive 0.9 divided by 100, and then times 100, so we end up with 0.9% error. And does this make sense? It does. Are precise measurements always accurate? And hopefully you can answer this question, and that answer should be no. To be precise, they are just close together. Does not necessarily mean that it is at the accepted value. This is going to be the hardest part of this section for sure. It is doing significant figures. And lucky for you, it doesn't take off full credit, but it does take off some. So we must use significant figures anytime we're doing a calculation in lab, in class, and it has to be reported correctly. So if you look at the thermometer, you can read that it is marked to the nearest degree. If I were then to read it, I would estimate the value between 22 and 23. And since it's very close to 23, I would maybe call it 22.9. That last digit is estimated because there's no markings. So between the markings is your estimated digit, and that is where your significant digits or your uncertainty lies. So the first digit, the 2 and the 2 are known. whereas the 9 is estimated. In fact, you may estimate it at 8. That's also an acceptable answer. So, significant figures in a measurement include all of the digits that are known plus the last digit that is estimated. So, we must report them to correct number of significant figures. So, we have rules for significant figures, and it's based on what kind of instrument you use to measure. If you measure this door with just a meter stick, you would only know kind of one decimal place because it's not marked in between. If it's marked to the tens, you would know it a little bit better. And if it was marked to the hundreds, then you would know it even better. Or to the ones. And then you would be able to give me 1/10 of a decimal. So if we look at our rules, and you want to write these down so that when we go over it in class, you have them. Every non-zero digit is significant. Doesn't matter where it is, non-zero digits are significant. In fact, significant figures really are all about how to deal with zeros. Zeros that are between two non-zero digits, like 7003. They are what you call captured zeros, and they are significant always. Zeros to the leftmost appearing in front of non-zero digits are not significant. I call these leading zeros. So in the case of 0.0071 meters, those 3 zeros listed in this number are not significant. If I were to put them in scientific notation, they would disappear. If we have zeros that are at the end of a number, we can do that 2 different ways. So here's the first. If they are after the decimal point, then they are significant. In all 3 of these cases, we have final zeros after a decimal point, and they would be significant. So each of these numbers has 4 significant figures. If we have final zeros, but there is no decimal point, then the zeros are not significant unless they would be captured between 2 digits. So 300 meters has only one significant figure, 7,000 meters, 1, 27,210 meters has 4. The zeros in 300 meters would be not significant, but if I needed to write it in such a way to indicate those 2 zeros were significant, I would go to scientific notation. Because scientific notation, if I write 3.00 times 10 to the 2, is indicating both of those 2 zeros were measured. And that's what a significant digit is all about, or a significant figure, is did you measure that 0 or not? So there are 2 situations where numbers are unlimited in terms of significant figures, and that's if we were to count. There are 17 desks in my room. No matter how many times I count it, no matter where I look, I won't find some little portion of a desk sitting around, and so it's a counted number and it's infinitely significant. The second is any conversions. If you're using something like 60 minutes equals 1 hour or 100 centimeters equals a meter, then it is infinitely significant, and we will not use those conversion factors to determine our significant figures. Significant figures come only from measurements made. So, the winner of a 100-yard dash finishes in 9.98 seconds. And the second place had 10:05. How many significant figures are in each of these measurements? Is one measurement more accurate than the other? Explain your answer. So, there are 3 significant figures in 9.8, but there are 4 in 10.05. Both were made equally accurate because they both have the actual time of the runner to the 100th of a second. Counting significant figures. So, how many significant figures are in each of these measurements? Go ahead and pause this video and write your answers down, and I'm going to go over them very quickly. I'm not going to spend a lot of time on this because you will have lots of questions in class. So A should be 3, B is 5, C is 5, D is infinite because it's a counted number. I counted how many meter sticks I had. E would be 4. The first 2 zeros are not significant. The 0 between the 7 and 8 is, and the final 0 is. And F would only be 2. So, hopefully that helps you. This is, you might want to pause this if you're having trouble with that, and it'll go through the rules that you need to apply. So, I am going to stop here, and we will talk about calculations and significant figures on the next video. Talk to you later.